And let me see. Something.
Okay, hi everybody, welcome. Our colloquium speaker for today is Karim Thebault. Karim is an associate professor in philosophy at the University of Bristol. Previously, he was at the Munich Center for Mathematical Physics. He works on questions in the foundations of physics, such as the problem of time and classical and quantum theories of gravity. But today, he's going to be talking to us about model-based explication and quantum singularity resolution.
Thanks, Helen. Thanks for the invitation. It's really wonderful to be here. I hope you'll forgive me for starting slightly kind of narratively in the middle of things, because the project I'm working on, I'm kind of temporally in the middle of things. So some of the stuff I'll talk about is what I'm working on right at the moment, which is what I'll talk about first. I'll also talk about some project I've worked on probably about 7 or 8 years to do singularity resolution in cosmology. That'll be the bulk of the talk, pretty much. And then I'll kind of end, seeing as we're in the Black Hole Institute, by talking about stuff that I'm kind of looking towards doing in the next few years, highly dependent upon certain grant agencies giving me some money to actually do it. But I've kind of started doing the kind of first steps towards the Black Hole project kind of recently in the last 6 months. So I'll talk a little bit about that. But I kind of like slightly kind of in medias res, like in the middle of things when I'm approaching the talk, is I also think kind of leitmotif for how I think we should do philosophy of physics, or how philosophy and foundations of physics should engage in the kind of practice of science. So a lot of what I'll be talking about during the talk is this idea of explication, which is really just a kind of fancy philosopher's word for trying to make a concept clearer or more precise. And so that's exactly what I take to be the project of philosophy of physics, or one of the key projects of philosophy of physics, is to work with physicists on making the concepts that they need to make more precise, and the concepts that they're using at the moment, which they need help kind of sharpening up. So this is kind of like inherently work in progress, because I take that to be the way that philosophy should engage with physics, is to do things with kind of pragmatic, kind of as you go approach, kind of refitting the ship of science, or we're all kind of sailing in it at sea. So I'll talk first about this idea of explication, as I said. And so by contrast, I mean, there's kind of a little bit of debate over it, and it's far from settled, and it's a little bit complicated, but we at least have candidate definitions for singularity, theorems for definitions of singularity in classical general relativity, whereas in quantum theories of cosmology or quantum theories of gravity, we don't have clear singularity theorems, we don't have clear resolution theorems. We don't even know what the domain is. We really mostly play around with very simple models, which is what I'll be talking about. And we obviously have no empirical data about quantum gravity singularity effects.
Do you mean the Big Bang here? Or what do you mean by quantum cosmology singularities? The Big Bang?
The Big Bang would be the classical example.
Is there any other example?
You could get big rip quantum principles.
Oh, in the future. Okay.
Get anisotropic
Okay.
singularity. But the Big Bang is what I'll focus.
Okay.
And even at the level of these very simple models that I'll talk about, only the simplest ones are analytically tractable. So often you actually have to use numerics, and I'll show some kind of outputs of numerical work that my collaborator did later. But we shouldn't be kind of depressed or kind of pessimistic. We can still ask interesting questions. We can still produce results, often analytically. We can have a look at simple models that are singular classically, quantize them for finite truncations of theory in a well-defined way, and suggest that there are resolution results. And this has been something that people have been playing with for 50 or 60 years, particularly kind of impressive results coming from loop quantum gravity, loop quantum cosmology, about 20 years ago. Really what I want to point out at the beginning of this talk, and what we'll get to throughout it, is that there's a particular style of reasoning that we're using in this context. So we're using these very simple finite dimensional models, we're quantizing them, and then we're making inferences about the types of things that resolve singularities in general, or we hope to resolve singularities in general. And I'll kind of talk about this more specifically in a moment, but just think about this as a very general class of reasoning, that we have this simple idealized model of quantum cosmology, and we try to use it to kind of reason about the very early kind of stages of the actual universe. And this is something, obviously, it's very, very familiar to different areas of physics. But there's different types of reasoning, I think, that are important that we can consider.
Very familiar, but very often unsuccessful in misleading,
Exactly.
right?
Exactly.
We know few examples where people,
It's a spherical cow problem, right?
well, we know a few examples where people guessed how things should work.
Exactly.
Read some reasonings, but
I think it can
one
mislead
can't
us
conclude from those examples that it's usually a successful
completely.
approach,
I mean, I think you need specific arguments.
especially when there's no small parameter involved.
I agree. Absolutely. I mean, I think you need very specific arguments that, like, let me get to it. Basically, there's a principle that we need. It's something to do with the stability of the kind of process of adding back in the features. That the result that we're trying to infer about the real system doesn't sensitively depend upon the things that we've idealized away in the model. And so we have some realistic model, we have some phenomena, and we can't kind of tractably solve this model to make inference about the phenomena. So we use some simplified version of that realistic model, usually involving reduction of degrees of freedom via symmetry. And we make some inference about the phenomena based on this. This is kind of standard like framework for the kind of things that we do in both theoretical physics and in experimental physics. So a simple example, we're here. We can imagine the realistic model would be a model of a black hole as a collapsing matter shell. The idealized model would be a short shell black hole, and the thing we're trying to make inferences about is a real black hole. And we don't want the features of the kind of collapsing matter shell, or if the inference sensitively depends upon features that we've removed, then we might be suspect of the inference.
Where do simulations fit in?
So
Sort of numerical implementation.
in the cases I'll talk about, for some properties, we need to even use simulations to do this relationship.
So it falls somewhere in between.
Exactly. And so there's been lots written about idealization and symmetry and principles of using models to make inferences. I think probably the two of the nicest treatments are by John Earman and Sam Fletcher. John Earman, kind of quite a few years ago, wrote a paper in which he kind of described a principle that's been subsequently called Earman's principle, which roughly means that a genuine kind of effects, we shouldn't make inferences about genuine effects from a model if those effects disappear once we kind of remove the idealizations of the model, which I think is a reasonable principle. Sam Fletcher talks about the principle of stability, where he kind of links it back to work by Poincaré and Duhem at the beginning of the 20th century. And that principle roughly is that it's a necessary condition to infer properties from an idealized model, that those properties hold the models kind of relatively similar to that model, so that models that are just slightly different to that model, the properties don't disappear. So I kind of want to propose something along similar lines, that this function of giving us kind of model-based understanding, it requires that the properties themselves are stable under de-idealization. So basically, when we add back in the relevant properties, we have reason to expect that the inference that we're making doesn't kind of fall apart from that process of de-idealization. And what I want to do is pick out 3 different notions of model-based inference. So the one that most people are talking about, and the one that's incredibly difficult to do, and I'm not really going to fully confront, but I'll talk about it a little bit at the end of the talk, is extrapolating. So most obviously, in the case that we're going to talk about, if the singularity is resolved in a very simple model, will the singularity be resolved when we de-idealize, we add back in the relevant structure? Most importantly, most of the models we deal with are spatially homogeneous, and we want to know if we introduce inhomogeneities, would the singularity resolution result disappear? So this is kind of a standard thing. A kind of related idea would be the kind of explanatory use of the model. So particularly lots of singularity resolution models don't just give us an implication that singularities are removed, they also give us mechanisms. So we want to think, is the relevant mechanism dependent upon idealizations, or does the kind of mechanism, for example, in loop quantum gravity, appeal to discreteness? Is that sensitively dependent? Is it kind of result of the idealizations? When we undo the idealizations, does that disappear? So these are quite familiar notions, but what I want to talk about here is actually a much more basic notion. So I've said singularity resolution, that singularity resolution, the other, right? But what is singularity resolution? What is the concept? What do we mean when we say the singularity is resolved in the quantum theory? And when I first got into this kind of literature, I guess about probably about 10 years ago now, it kind of seemed really confusing to me that almost no one seemed to agree on what it meant to resolve singularity, at least in the canonical literature. And so what I want to do today is really talk about the idea that we can use the simplified models, and particularly the model I'll talk about, it's called mini superspace, which is just really a Friedman cosmology. In this context, just to actually refine the definition of singularity resolution. And so the project is actually using the simplified model just to refine our concept. And I think we need to do that before we can do the other things anyway. And I contend that the scientists will profit from the exercise of trying to be more precise about what they mean by the actual kind of content of a claim of singularity resolution. Yeah.
Well, if you're talking about the scientists, currently, most of the cosmologists are signed up to the concept of inflation, where you can have chaotic inflation that generates many types of universes. That's what, and there is this bigger space-time that is the multiverse, where that's kind of the folklore. And there is no singularity.
So my understanding is that you still get geodesic incompleteness for inflational cosmologies, that you can extend the Penrose-Hawken results to inflation as well. But that was my understanding.
When is the singularity?
So that there's still a
Oh, before inflation.
exactly.
Yeah, what happened? No, so if you have chaotic inflation, then it happens all the time. The vacuum fluctuates and generates new universes, but the universe never starts from a Planck singularity kind of.
So
yeah, but
so
anyway.
Either that, or the other paradigm is that the universe becomes highly quantum and we don't know how to describe it, and we don't know what a geodesic is.
Sure. I mean, that's essentially what I want to talk about today, is that so I'm not going to talk about inflation. What I'm going to talk about is very simple models of the Big Bang, where you quantize degrees of freedom and you get a bounce. That's the kind of general structure of the quantum singularity resolution.
But without the theory of quantum gravity, how can you get a bounce?
I mean, we don't have a theory of quantum gravity, but we know how to quantize there are various proposals to quantize finite dimensional truncations of general relativity, because these are essentially particle theories, because they have a kind of reduced set of degrees of freedom. So I will show you a model in a second.
There are such proposals, and there's absolutely no reason to think they have anything to do with anything.
I mean, you're grist to my mill, right? So the question is, when can we make these inferences from these simple models to the world?
When
right?
there's some plausible explanation that the simple model might describe something.
I mean, suppose you want as a philosopher to develop a product that will be consumed by scientists, right? That's your goal, a product that is consumed by scientists. You need to listen to the customers.
Sure. My customers here, but I mean, perhaps you guys are not my customers. But maybe you will be by the end of the talk, right? My customers here is the canonical gravity community, right? This is the community that I trained in, that I understand the way they think about it, right? If you want to say, I don't want to even get on that train, that's fine, right? I can see good arguments both ways. But people have been playing these models since 1967, right?
And nothing has come out.
There are thousands of papers.
I know them, and nothing has come out.
Yeah.
But I mean, my point is not to convince you that this is the right program. My point is that if you're interested in this program at all, one should hope that they could at least have a clear definition of what it means to resolve the singularity. And let's hope if the project that I have of trying to have a clear definition of what it means to resolve singularity will be useful in other contexts too, right? But I mean, I'm definitely not here to like kind of redo the string laws or convince you that you should be.
It's not even about string theory, it's about something that is logically plausible with a small parameter.
You-
I don't think Karim's trying to defend this program truncation.
No, he's
just
selling us a
supporting it.
used car. We don't want
No,
this used car.
but he is advancing it as a kind of paradigm in which we can have discussion on these issues. And I would deny it even.
I mean,
though
these
it's-
are these are
You don't think
toy
it's
models.
just a demonstration of an
I don't think
example?
it demonstrates anything.
I think they're toy models for quantum
Yeah,
what
but
quantum
you know,
gravity
there's some
could
of
be.
us who don't
Depends
know
on-
anything about
It
this.
depends on
I-
if you approximate the Higgs boson by, you know,
Andy.
the jungle gym.
Andy, most of the people here don't know what he's going to talk about. We just want to know what.
Let me give the talk and then we can have.
Yeah, I think so.
Andy, some of us haven't
I
even
don't
gotten
think
into the
it's important.
store, you know?
Well, Andy's trying to save you time.
Okay, I'm going to carry on now. I mean, honestly, compared to giving a talk at PI, this is really gentle.
Oh, okay. Okay. Andy, you may go ahead.
Let's reclaim.
So the project is to try and take a concept that's vague in the scientific literature and make a more refined version. And it kind of follows from Carnap, these two kind of really wonderful philosophers, Howard Stein, unfortunately died recently, Andre Carus. They kind of talked also about the idea of refining concepts of explication as something that we should understand in a kind of pragmatic context. So we're trying to re-engineer a concept for scientific use, not based upon some kind of in-principle definition of this is what the concept should be. And so the idea is to do this for singularity resolution. But in order to kind of get to the point where we're actually talking about what it is to refine the concept of singularity resolution, we at least have to go think about a model of singularity resolution. And so what I want to do is jump back in time before I thought about this project to a physics project that I did with collaborator Sean Gribb for a number of years to try and understand or to try and develop a particular approach to singularity resolution, which is really to do with the problem of time and quantum gravity. And so in classical case, we have these two definitions of singularity. One where we have incomplete inextendable causal path-directed curves, and one where we have some kind of curvature pathology. And luckily, in the cases we're going to talk about, they'll basically run together. So we'll find that there's incomplete causal curves along which an observer will measure a curvature pathology. And what we did is basically develop an approach to study classical models of the Friedman universe with these features in a particular approach to quantization, which is based on a slightly different way of thinking about the way time works in canonical gravity. The first kind of starting point is really just to recognize that in this kind of finite dimensional truncation of general relativity, if you move to the Hamiltonian formalism by the kind of ADM action and then doing the Legendre transform, you actually end up with quite a simple Hamiltonian. And so we have just assume a finite dimensional homogeneous isotropic universe, and we have a scalar field which is massless, vanishing spatial curvature, but the cosmological constant we don't set to zero, which is really important ultimately for the model. We basically then only have in the phase space 2 degrees of freedom in their canonical momenta. We have a spatial volume degree of freedom, which is basically the scale factor cubed, and then we have the matter field, and then they each have their momenta. And so we end up with this kind of fairly simple kind of Hamiltonian with these kind of square momenta terms and a cosmological constant. And because this is a general relativity, this is a constrained Hamiltonian theorem, which in the kind of standard approach developed by Dirac would mean that we'd have a kind of Wheeler-DeWitt type equation. So because it's a finite dimensional theory, essentially on R plus, sorry, let me go back. So you can show that this has a singularity in the senses that we talked about before. And so that singularity is going to be at v equals 0, just as you would imagine in the classical theory. And like I said, essentially this is a finite dimensional classical theory, so we can construct a Hilbert space and start exploring the quantum theory. And so there's a couple of problems that you run into. You can define the inner product, but you find that the momentum operator doesn't have a self-adjoint extension. But luckily, Isham studied this problem quite a long time ago and found a way of canonically transforming into these log variables, which in that chart we can find self-adjoint representations of all the operators. So we can basically build a quantum theory. We have a Hilbert space, we have self-adjoint operators. The kind of basic move that Sean and I proposed is that by treating the cosmological constant as a constant of motion rather than a constant of nature, you can essentially construct something that's following the same route as Wald and Unruh from the late 80s towards a unimodular theory where you have a Schrödinger type equation, where essentially the cosmological constant is the canonical momenta to a time variable. So you basically rewrite the Hamiltonian such that you get a Schrödinger type equation. And the Hamiltonian is not essentially self-adjoint, but you can find the self-adjoint extensions by opposing boundary conditions. And then you can use this theory to build solutions. And the solutions will evolve with respect to this special type, unimodular type route. And you find, or Sean found after quite a lot of work, that there's a particular class of Bessel functions that you can use. And you basically get kind of ingoing and outgoing waves that will interfere around the singularity. And in the kind of, for the positive, you get both positive, the general solution has both positive and negative lambda kind of parts. And you find that the positive family have a kind of late term limit, which goes back to the Friedmann cosmology.
Your lambda goes to minus infinity, but that's not, I mean, these are sick theories that have arbitrarily negative cosmological constant because they violate the NEC, the null energy condition. Lambda cannot.
We will violate the energy conditions anyway.
Yeah.
So we're integrating over all these values, right? So they're not.
So you're not worried about it being arbitrarily negative, lambda?
No, I mean, that's just part of the parameter space.
Okay. But the theories are not valid according to.
I mean, these are going to be very, very deep into the quantum regime close to singularity. We won't see them.
Okay.
Right? The idea is that essentially we're in a super selection sector where the value of our cosmological constant through decoherence gets kind of selected. But the full quantum, it's kind of like think about it in a many worlds space, right? The full quantum theory would have all values of lambda.
So is this a 3+1 universe?
Yes.
Okay. But you're working around a homogeneous isotropic.
Exactly. But so Gillen and Turek did a path integral version of the same model.
Okay.
And so in some sense, this model's been reinvented 3 times. So it's in Unruh and Wald 1989, and it's in Gillen and Turek 2016. What we did and what Gillen and his collaborator did later is just actually explicitly construct the solutions and look at their behavior. And what you find is that essentially there's an advantage over the standard Wheeler-DeWitt quantization because you don't because of the uncertainty principle, you find the expectation values can't kind of blow up to infinity like you can in the Wheeler-DeWitt theory, where you take out one parameter as a time value, and then you find that essentially the singular behavior in the expectation values kind of the expectation values follow the classical values up to infinity. Whereas in this theory, the kind of bouncing effect that you get basically diverges from the classical solutions once you get close to the singularity. And so the kind of simple case in which you can kind of smooth out a lot of the structure, if you imagine, so it's time symmetric, at very kind of, let's say, just pick conventionally an hour of time, at very, very early times, you basically take a Gaussian state, you evolve it into the singularity, and you find interference between kind of ingoing, outgoing waves, and then the kind of bulk of the distribution bounces back out together. And so you get kind of a very nice cosmic bounce. You can track the expectation values for the scalar field and the volume, and you find that you get a kind of parameter dependent turning around point where the volume reaches some minimum and then bounces back. So you don't find, you approach zero volume and you don't find kind of divergent expectation value.
Where is Newton's constant in all of this? Because the Planck scale should be somewhere.
In N.
Okay.
And the cosmological.
So the Planck scale is implicit in this?
Yes. Yeah. So I think basically all the variables have been redefined to remove the dimensions.
Okay.
And so we were very happy with the result. And that was great. How am I doing with the time?
Approaching 30 minutes.
Right. But then, I mean, the question is then, is having finite expectation values actually a good criterion for singularity resolution? And I kind of was a bit taken aback by the fact there was no clear kind of answer in the literature about what it meant to resolve singularity. So I thought I'd have a look into the problem. And so what I did is write a review article where I essentially considered what people had said in this huge literature and try and make some sense of it. So I looked all the way back. The first paper really of trying to deal with this question is from 1967, which is Bryce DeWitt's really famous first derivation of the Wheeler-DeWitt equation. And I really focused on papers with two types of idealized cosmologies, ones that are isotropic and homogeneous, and ones that introduce anisotropies, so the Bianchi models. There are some treatments of slight extensions where inhomogeneity is introduced as well, which are called MIDI superspace, but I didn't look at that many of those. And essentially what I tried to do is look at what they meant by singularity resolution and what criteria they're either explicitly or implicitly kind of appealing to. And I think the biggest and most kind of basic thing that came out of this was to actually think exactly the question, the point that came up before. Given that we don't have concept of geodesic, what do we mean by the kind of dynamical pathology? What's the analog of the dynamical pathology in a quantum theory? What is it for a quantum theory to have the thing that's similar to incomplete geodesic? It's kind of seems fairly sensible to think that if we want to understand what the analog of a curvature pathology is, we can use the correspondence principle and look at the quantum operators that are the kind of quantum correspondence to the things that are classically divergent. It's not quite clear, or it wasn't quite clear to me what the best way of approaching the question of dynamics was. The other thing that, without being rude, is worth noting is that sometimes it's not even clear when people are using these definitions whether they're taken to be necessary, sufficient, or necessary and sufficient. So just a simple thing to actually do in conceptual housekeeping was to try and pick that apart. And then what I proposed in the paper is to actually use this idea of stability. So for example, if a criterion only makes sense for the mini superspace model without the anisotropies, but then when you introduce anisotropies, the criterion no longer even makes sense or doesn't apply, it's not stable. I also, as I said, use some kind of mapping back to classical notions to be a kind of criterion for or a condition for the criterion to make sense. I think also that approaches to singularity resolution are very heavily dependent upon particular interpretations. So there's some that only really make sense for Bohmian interpretations. I think that's not probably a very good criterion. You have to be a Bohmian for it to make sense, or you have to be an Everettian for it to make sense. And then I also looked at obviously counterexamples. And one of the things that's kind of
quick point of clarification, when you say bounds, I mean, Is this a bounce that will give you a cyclical universe later on? I know we are not worried about it later on,
So
but,
in our case, no.
okay.
Other cases, yes. I actually wrote a different paper about the Turek. You can never say it.
Steinhardt.
Steinhardt.
Yeah.
Ekpyrotic universe. So they're related in some ways, but at least in this case, a bit different. And I mean, these models, as it stands, are not going to deal with the problems inflation society.
So one other question before you proceed. You showed a result earlier. Was that for anisotropic problem or was it an isotropic problem?
Isotropic.
Isotropic, okay. Right.
So that model we haven't extended to anisotropic.
Yeah, because that's the problem, right? Anisotropy just grows when you go
But
back.
there are, I mean, people have studied other resolution models,
Okay,
which they apply to the Bianchi models, which have anisotropies.
and
So there's a
they,
family of them.
okay,
People have.
and they bounce?
Yeah.
Okay.
So I mean, I think we don't expect it to be that difficult to do the extension. We just haven't had time to do it yet. There's no reason in principle the same mechanism shouldn't work for this. They have done this for loop quantum gravity. They have done their mechanism, which is slightly different. They have applied that to anisotropic. And so one of the issues that I'm kind of skirting around, right, is that there's a difference between we're evaluating criteria, not mechanisms. And so if I want to think, is a criterion stable? The question is, can I still apply the criterion to a more complicated model, not whether I get the same result? The perfectly good criterion, as long as it makes sense in every context. But for a mechanism, you really want it, if it's a genuine resolution mechanism, you want the mechanism to be stable. So we're focusing on this kind of stability of applicability. So the idea is to kind of show the diagram again. We develop a definition of what it means to resolve a singularity for the simple model, and we want to kind of hope that the criterion of what it means for the singularity to be resolved is stable when we move to the more complicated context. And so I evaluated 9 criteria. These are the best I could come up with. So I'll just go through some of them. The simplest one the people in loop quantum cosmology use is basically that the operators are bounded, particularly the volume operator. Yeah, volume operator. Inverse volume operator. The one that I've been talking about already, finite expectation values. Another one which ends up being problematic that people use is just avoiding 0 in the expectation value. DeWitt's original paper, he proposed just the wave function vanishing. Klaus Kiefer updated this with a conformal version of it. Martin Boswell has a kind of idea that's very similar to hyperbolicity in terms of like theory of PDEs, but extends it to quantum. I think Giddings and Morolf proposed essential self-jointness as a criterion. People have also variously talked about unitarity, and there's a kind of more complicated idea that involves the kind of particular type of clock you use to deparameterize. So this is a lot of fun. I went through all of them. I ended up kind of knocking out quite a lot of them because they weren't stable or involved kind of unreasonable interpretational moves or unjustified interpretational moves. So we end up with 4. And so the concept of singularity resolution in my kind of explicated form ends up involving all these different kind of conditions. So the idea is that it's a necessary condition to have finite expectation values and be unitary. It's a sufficient condition to have bounded operators, and it's necessary and sufficient to have this quantum hyperbolicity idea, which is essentially that you can evolve the equations of motion for any surface. So unitarity is a kind of slightly weaker condition, which means you have well-defined propagators essentially. Whereas quantum hyperbolicity means that you're going to be out, there won't be any surface you can't kind of evolve the solutions through, which I take to be the analog of having kind of not having incomplete inextendable geodesics. Whereas the analog of removing the curvature pathology, I took there to be it's necessary but not sufficient to have finite expectation values, because there are models of finite expectation values that seem to still have the necessary condition not sufficient condition. And a sufficient condition with bounded operators, because there are models of unbounded operators that still have behavior that doesn't look pathological.
Could you explain with this quantum hyperbolicity? So what you're saying, the wave function can be evolved from any initial condition.
Exactly.
Without reaching any pathology.
Exactly.
That's it.
Pretty much. I mean, it's a little bit, the way Barjot defines it is a little bit more complicated, but that's what I took it to. I mean, it's actually quite difficult to show. The problem of it is very difficult to explicitly show it's satisfied. But I think it did seem like a very sensible condition to me.
I mean, it's an assumption.
So it's a,
Definitely.
if this is true, that's basically necessary and sufficient for singularity. But it's quite difficult to actually show.
Well, it's just like saying if the singularity doesn't exist, then it doesn't exist.
Yeah.
So
Right. Yeah. But there's a singularity in some wave function.
But when some people say the singularity doesn't exist, they mean this, right? So
Yeah.
okay.
I'm not saying I've done the most important thing in the world. I just think I've done something that helps people be a bit clearer, and sometimes that's helpful. Okay, so seeing as we're at the Black Hole Institute, I've started to think about how any of this relates to black holes. And I mean, the nice thing is that I found out recently that there's actually quite a lot of structural kind of relationship between black holes and these simple cosmological models, which perhaps maybe this is a reason to care about them. But you can find different ways of approaching the maths, particularly of the interior region of black holes, by using techniques developed in cosmology, whether you care about those cosmologies or not. So you find both the mechanisms and the kind of criteria, you can move them into the black hole context, or people have moved them in the black hole context. But in particular, what you find is because they're have very high degrees of symmetry, there's a kind of structural mapping between the cosmological metrics and black hole metrics, particularly in the interior. And so that means that you can actually use some of the cosmological models to study the interior of black holes. But we should also, of course, be careful, because in the end, black holes are very different cosmologies. And we shouldn't think that kind of just because the simple models in each case have the same structure, that the way that we can make inferences to the de-idealized system, to the real physical systems in each case are the same. And so on the one hand, I'm quite happy, because it seems like a lot of the work and a lot of the ideas that I've done, other people have done on singularity resolution, quantum cosmology, have a kind of home in black hole physics. On the other hand, I think there's this kind of general problem about idealization means that we have to be quite wary.
No,
So,
but even the idealized problem is interesting in the black hole case. So are you saying that the quantum Schwarzschild black hole will bounce?
on some models, yes.
Will bounce, and then what? Does it come back out?
White hole.
Oh, it becomes a white hole.
Exactly.
Oh, that's the point. I see.
Yeah.
Okay.
And
Okay.
so I'll show you a model.
Okay.
I mean, in fact, I'll show you the same model again in a second.
Right.
And so the two papers that I've looked at so far, I mean, like I said, in context, for the other project, I looked at probably about 100 papers. For this project, I've looked at 2. So I'm just starting. And yeah, so hopefully someone's going to give me lots of money to work on this for a few years. It's really fun. But if not, it'll probably take me another decade to get through at this rate. So I looked at 2 papers, one by Hussein and Winkler from the kind of early days of the kind of loop quantum gravity success on these projects, 2005. And then one from Stefan Gillen, who I've mentioned before, that's really kind of version of some of the stuff that I talked about using unimodularity, and which is only from this year. And so Hussein and Winkler, they use a Schwarzschild black hole with a massless scalar field. It's a very simple model. It's stationary, asymptotically flat, spherically symmetric, minimally coupled massless scalar field, and they put some conditions on it. And what they show is basically that there are functions that you can define on phase space that diverge classically, as you'd expect, right? And if we take we've used the condition that we talked about before, as boundedness of the divergent quantity as a sufficient condition, then there's a particular approach to quantization based upon something called Born compactification that will allow us to show that the relevant operator will be bounded. And so what they point out is that there's basically a general class of discrete quantizations, a bit like the Ashtekar variable quantization, that allow you to control these singularities. And so in this case, you can appeal to this kind of build this Hilbert space on the Born compactification of the real line, and then show that this operator, which is classically divergent, it's the analog operator in the quantum theory is bounded from above, which means that we remove the divergence. So it seems like the kind of schema that I've developed for singularity, for defining singularity resolution, is working for this case. The sufficient condition for local curvature singularity resolution is met. The second case, which is perhaps more exciting and very recent, is looking at this particular interior black hole metric, which is a planar ADS black hole that has a planar horizon that's asymptotically ADS. And what Hartnell found a few years ago is that you could actually find an ansatz for this metric, which has this form here, which is kind of mappable into the mini superspace theory we talked about earlier. And so this metric he shows is equivalent to the standard one for planar ADS black hole. And it has the horizon as k goes to minus infinity, b to 0, and singularity as k to plus infinity, b to 0. But then what he shows, which is really remarkable, is that because you're in the interior, you can interpret r as the time coordinate, put this back into the Einstein-Hilbert action, and then you can derive, through the standard canonical analysis, you end up actually deriving exactly this Hamiltonian I gave you earlier. This one. This Hamiltonian here. Only, of course, but the variables are now like structurally the same, but they're actually
It has a
representing.
lambda?
No, lambda is negative, it's anti-de Sitter, so it's not the real universe.
Oh, I see.
Yeah, so it's a hypothetical.
It's a model, it's a model. I mean, why they didn't, so I just was talking to Sean, my collaborator, and he was like, why didn't they do positive lambda? This should work. And so we don't really understand why they didn't. So
It would work the same?
I can't see why not. That's what we're going to do as soon as we get time. But in any case, what they show, they've done the numerics, is that you get the same results. You basically get a bounce. This is, remember what I was showing you before were simulations of the positive lambda, where the semi-classical state goes into FLRW. This is the negative lambda, which are actually these family of bound states, which weirdly have a quantum analog in something called the Ether model effect. But in this case, what you end up with is cyclic bounces with transitions between white holes and black holes. And so that's kind of interesting, it's kind of weird.
Each one in a different universe, right?
I mean, this is the universe.
Well, but we don't see white holes in the universe.
No,
I mean,
no,
this is.
No, but I mean, if you don't go into the black hole, you don't go.
This
to
is
the
inside,
clouds.
right?
Oh, it's all inside?
Yeah.
So each black hole, white hole pair has a different asymptotic region.
And so it's very weird. It's very interesting.
It bounce and you come out in some other universe. Then
Yeah.
you bounce, you go out in. yet
Just
another-
like in the maximum extended pair diagram
Good. Or, yeah, that's not Armstrong.
or Rice-Renoir.
Yeah, okay.
But where is this? The
There's
other,
no singularity in Rice-Renoir also. If you put electric charge, then you can stay in the domain of validity of the Einstein equation. But of course, it's unstable to small perturbations.
So I mean, that's very interesting. I don't know these solutions very well. I just found it kind of amazing that we can essentially reuse the quantum cosmological model in this context as well. And there seems to be quite a kind of interesting families of mappings, like I said, between these quantum cosmological models and interior black hole models. So that gives us a way of bringing the resolution criteria with us. In this case, we again get unitarity. I'm sorry, I should say this is quite important, that the standard approach to time in quantum cosmology uses one of the physical parameters as a clock for the others. Developed a long time ago, particularly popularized by Karim Thebault. Under that approach, there's no guarantee that the evolution will be unitary. However, if you do this unimodular clock deparameterization, or what we call relational quantization, you are in general guaranteed that you'll get unitarity. So there's a good reason to think that this particular way of approaching time in the theory is going to give you a unitary theory, and the extent to which you thought unitarity was a condition for avoiding singularities. It's quite nice.
And what about quantum hyperbolicity?
That we don't know.
Okay.
To show.
And why does a white hole turn into a black hole? You're saying that there is what it doesn't bounce, it just things are coming out of it.
So
So there is
this basically the quantum cosmology. I mean, in a sense, the thing that I find strange is the difference between a black hole and a white hole in this context is just the arrow of time.
right.
And so it just means that you get a turnaround between the kind of
Oh, so it's like a closed universe that ends up.
Which keeps bouncing.
I see. Okay.
Backward.
I mean, it wouldn't be the most, I mean, maybe it would be fun, it'd get a bit repetitive after a while. So the concept seems to work. The physics is very different. It seems like so far so good. The project of having a better notion of singularity from cosmology works as well.
So this is just in the interior of the black hole, this thing is going on.
Yeah.
I mean, I know it's not meant to be realistic, but.
So this is ultimately the problem, right? Is that so far so good, but to what extent, how would all this work in black holes formed by collapse? How would this, to what extent can we make inferences that are reliable from these cases to the universe we actually live in with late de Sitter rather than anti-de Sitter? And most importantly, what you find is that when people defend the stability of extrapolation, right? When people say, no, this result will apply in other cases as well, they typically appeal to the BKL conjecture, which basically means that as you approach a singularity or what large class of singularities classically, you get behavior that increasingly looks like a kind of local Bianchi universe at every point. And the claim is then, if you can resolve a singularity in, and as I say, you do similar things for a black hole. If you can resolve a singularity in a model of that feature, that because that model asymptotically represents a wide class of model of physical systems, you somehow resolve the model generically. But the problem that Boswell and I pointed out is that, of course, that only works asymptotically. And if you're bouncing before you get to that region, then that's not helpful at all. And so it's not clear what kind of arguments you can give that these resolution proposals will kind of be stable under a wide variety of models which include back in the feature. And I think that's, for me, the fundamental kind of project of singularity resolution, to actually show that this is in any way relevant to real cosmologies where we have inhomogeneity. And so I kind of leave you where I started you, like in the middle of it, and try to work out what's going on. Thank you very much.
Okay, we had plenty of questions throughout, but any questions for Chris?
Yeah, you kind of mentioned this Bianchi collapse problem, which is an anisotropic problem. So what exactly have they proved? You say that it is a stable bounce?
From my understanding, in the Bianchi models, you can do a very similar result. So, for example, you can show in the loopy approach, you can show that the volume operator, the inverse volume operator, is bounded from above in the Bianchi model.
Okay, because coming from a classical picture, see the isotropic model, good, collapses and goes to a singularity. The anisotropic model must make pancakes and, axes, and so it should be a triple bounce of some sort. Each of the axes will bounce at a different time. I'm just wondering, what is the corresponding quantum picture? What is, does it go through three
So I don't
avoided
know.
bounces?
That's very
or-
interesting. I don't know. I mean, I'd have to.
What do you
look at the
think of?
models again.
Probably just one.
Classically, we know the Zeldovich pancakes.
Yeah,
and
we
all.
actually wrote a paper about anisotropic.
Uh-huh.
If our universe was anisotropic to start with, it
Yeah.
will become isotropic later on.
That is sure.
Yeah.
It's the back
But,
problem that's. the
so it's
problem.
actually non-intuitive. You can check it's with Herzberg,
Yeah.
just from this year. It's a very interesting question. Was not
Yeah.
addressed.
So the question
Well,
is
not like BKL, where it showed that the universe becomes chaotic.
exactly.
Yeah, that
Yeah,
makes
And
sense.
so that's the opposite of this. Every degree of freedom is important. It doesn't simplify to a few degrees. of freedom.
Okay, yeah, yeah,
That's what one generically.
that makes sense.
That's
right.
called mixmaster.
Exactly.
Yeah.
Mhm.
Yeah.
And the quantum version of that will somehow avoid all singularities.
Who knows?
Well,
So I mean, the question really is.
no, I don't think, I mean, I don't think we have no idea what, everything is strongly coupled.
Yeah.
There's been essentially no insight from stringing models or any models, in my opinion. And I don't think we even know that, that the universe continues. What are we really, what is,
Well,
the
bounce
Big
means,
Bang, the
yeah,
Big Bang suggests that you had nothing and then
Nothing.
something came. So is it even described by quantum mechanics? I think it's pretty hard to defend that point of view that it's described by quantum mechanics.
right, but there are solutions apparently, at least for this, few
The
degrees of
solutions of equations that are not, there's just no reason to think they approximate the universe when it gets small.
Mhm.
It's a system of equations that doesn't even reproduce general relativity. At
Hold on,
long
hold on,
distance
hold on,
scales.
hold on. That's not true.
Smolin showed that it doesn't, because
When? What? In what way?
there have been many papers written, because in the quantum theory, there's uncontrollable ultraviolet divergences.
In which quantum theory? In
Loop
you mean
gravity.
Luke quantum gravity. Okay, fair enough.
Yeah.
So I'm
So
not
it
talking
doesn't
about-
approach general
Hold on, hold on.
relativity at
We're
long
not talking about-
distances,
I
and then
wasn't
we
talking
use it
about-
at short distances. and
I
so
wasn't
it all-
talking about Luke quantum gravity, right? I'm not defending quantum gravity. I'm
I thought-
talking about a whole family of simple models for simple cosmology, which have a semi-classical limit of general relativity. I'm not talking about the program of quantizing gravity, which is a huge, ambitious, and possibly futile project, possibly, right? There has been a long tradition of playing with these simple models, and maybe they're not useful, maybe they are, but they do have but the only reason why we trust them at all is that they have semi-classical limit of Friedman cosmology or a Bianchi cosmology, right? So they're not completely, I mean, we have reason to believe that they're not completely useless. I agree, we don't have
I
good
don't
reason to
think we
believe that
have any
they.
reason to believe that.
And
What reason do we have to believe that there's just one degree of freedom important at the Big Bang?
I mean, to first approximate, we don't know. at
If
the
we
Big
look
Bang.
at it,
Yeah,
it looks
sure,
like a
sure.
fiery mess, right? We see it in the sky.
To first approximation, our universe is a Friedman limit, right? And the
At long
first simple,
distances.
look, imagine the first days of quantum mechanics and someone quantized a harmonic oscillator. And he said, look, this is nothing to do with the world that we live in. The world we live in isn't a harmonic oscillator. Why would we quantize this? That would obviously be silly, right? I'm just saying, we're like at the level of doing quantum mechanics in the very, very first simplest system we can possibly do. I'm not saying that that's going to be necessarily useful, but I don't think it just
But the conclusion that it bounces, a qualitative conclusion like it bounces, I think.
or
is
qualitative conclusion
completely
that matter
unwarranted.
is stable that we got from simple models in quantum mechanics early on, that turned out to work. It might be true in this case, it might not, right? But just saying we shouldn't do any of it, I don't think that's a good option either.
Maybe I can ask about I'm curious about the background commitments of the stability. So I'm wondering if one were to be given from an oracle some theory that say doesn't have the kind of stability that you're looking for, would you still take it? Like, would you still allow that? And if so, are you thinking about stability as a kind of pursuit worthiness criterion?
So I mean, I think it's an epistemic virtue. Theories that were radically unstable, it's harder to use them to make predictions, right? I mean, in some sense, a lot of this came from like Poincaré studying the stability of the solar system. And so, like, ultimately, it is hard to make predictions from, for example, from three-body models because they're very sensitive to initial condition, right? So it is something we have to live with, that there are wide classes of models that physically represent things that small changes can make very big differences. So I don't think we should reject them altogether. But I think the point is that we need to be very careful about the inferences we do make based upon simplified models, because we need to have some warrant to make the de-idealization. And I mean, often we find that when we can do this successfully, we have universality arguments that in certain circumstances, differences, we know that certain differences won't make a difference, and we can make these inferences. So I think like the other example is obviously the singularity theorems themselves, right? So in some sense, like I'd want to interpret them as stability theorems. So I guess what I would say is that it's a norm for finding ways of analyzing theories that are stable, as much as only choosing theories that are stable, because it's very unlikely that the kinds of theories that we're going to have will have these properties generically. But what we want to do is to be able to find qualitative ways of grouping solutions that are stable and making inferences from.
I guess I'm wondering about like stability of mechanisms seems less perhaps important in the final result, although it might be more on the pursuit worthiness versus stability under the kinds of examples that you just gave.
I mean, I think it could be a good argument that a particular mechanism isn't doing explanatory work that we thought it was, if it only works for very simple cases. And so if we find, for example, we find that only that like a singularity resolution mechanism implicitly uses a high degree of symmetry, and without that it wouldn't work. I mean, in some sense, this is what the expectation was the other way around with Oppenheimer and Schneider, that the singularity producing mechanism was highly sensitive to the spherical collapse. And we found out that was the other way around, in fact, that it wasn't. That's what Penrose essentially showed, is that it wasn't sensitive to the spherical collapse. And so, yeah, I think depends on the case, really, how we should think about them. But I think these are essentially, don't want to think about them as metaphysical principles, but as heuristic or methodological principles.
Just a minor, perhaps, question. So why would you, in this list you gave, why would you want to have non-zero expectation values in the first place?
So the idea is that we identify the Big Bang with the volume going to zero. And so that if we avoid the volume going to zero, we've avoided singularity. But the problem is you can get these pressure singularities that go without volume going to zero. So it's unclear why people ever, people still say this in the literature, right? People still say that the singularity resolve could be removed if v goes to zero, but that seems to depend sensitively on being on a quite simple model where the only singular behavior is attached to the volumes. But I mean, the kind of simple reason why you'd think that that is a singularity is that the energy density would diverge if you have finite energy and you have zero, the volume goes to zero. In fact, it's kind of physically intuitive, but you can get singularities that don't have that characteristic, so it's ultimately not good material.
There is a simple test of the conviction of the authors of these papers. If they believe the singularity is avoided, they can enter the biggest black hole and test it, right? If they really believe. Would you enter a black hole?
I mean, I think that the problem is that the spaghettification is not avoided.
Well, it depends when if the black hole is big enough, you can avoid the curvature, perhaps.
At the horizon.
At the horizon.
Well,
At the bounce.
At the bounce, it depends on the bounce. So if they have a model in which the bounce is large enough, yeah. So just ask them.
They will all
I mean, the
offer
problem
to
is-
go there, except how.
I mean, I definitely would trust it so far as to where the parameterization of the bounce, such that if you're relying on the numerics to work out whether you bounce before you get to get it.
Exactly. That's the question. That's Hamlet's question. To be or not to be.
Okay, thank you all. Join me in thinking through them. And then continue the discussion.